So, hello everyone. Today we'll start our third class. So, before going to the main content of today's class, let me just discuss briefly the things that we have done in the previous class. And okay, so in our previous class, we started our discussion from the formulation of uniform energy ladder. Okay. So energy ladder is a hypothetical concept. So here what happens, each of the energy levels are equally spaced. Okay, like here the energies are 0, E, 2E, 3E, so like that. So as you can see, all of the energy levels are equally spaced. The difference between between two successive energy levels are basically equal. And so for this kind of a system, we have calculated the partition function. There is a so for this kind of system, if you consider the degeneracy of each of the energy level is 1, in that case you have a very useful closed form of the partition function. Okay, so that is basically very helpful quantity to further evaluate other thermodynamic functions, basically for the system which shows this uniform energy ladder kind of a behavior. So for that, we first consider the formula for partition function, that is q equal to gz e to the power beta ez. Now from here, since we consider that the degeneracy associated with each of the energy level is 1, so that means we can write it as summation over j to the power beta ej. Now we can write it like this: q equal to 1 plus e to the power beta e minus beta e plus minus 2e plus beta 3e, and like that, so on. Now from here, since we know that 1 by e to the power beta e is basically less than 1, right? The mod value obviously much less than 1 actually. So for this case, we use the formula for binomial distribution, and from that, using that formula for infinite summation for a for a binomial distribution, so we got this closed form: 1 minus e to the power minus beta e. Okay, this is a very useful closed form of the partition function we got for the case of a uniform ladder. And using this formula, we can also calculate the population density in each of the energy state. We know the population density is generally given by pi equal to e to the power mean beta ei divided by q. So you got the q here. So if you substitute the value of q here from this expression, then you will get pi, or that is basically equal to ni by n, the fraction of particles into the ith energy level basically. So that is basically e to the power minus beta ei into 1 minus e to the power beta ei. Okay, this is a very useful formula. Then we also discuss some problem regarding it. Okay, after that thing, we have also calculated the partition function of a particle that moving in a 1D box. Okay, partition function of a particle moving in 1D box. Okay, so how we have done that? So for that, we use some previously developed result from quantum mechanics basically. So what happens is that in quantum mechanics, we know from the infinite potential problem is that if you trap the particle in an infinite potential well, in that case the particle used to have these discrete states of energy, right? And the expression of the energy looks like this: En equal to n square a square 8m x square. Okay, provided that the x is the length of the side of this box, and m is the mass of the particle. Okay. Okay. So if you able to measure these two quantities, so from using that two thing you can basically calculate this discrete energy level for a particle that is trapped inside a infinite potential level. Similar concept here also. So here also we start the lowest energy level at E1. Okay, for this case also. So for this case also, in order to calculate the partition function, we need the energy. So E1, the ground state energy is h square 8m x square. Similarly, E2 is 4h square 8m x square, and so on. And so one of the major thing that we consider to calculate this partition function for a uniform ladder system is that the ground state energy should be equal to 0. Okay, but here the problem is that since the ground state energy is not 0, so to make it 0 we basically subtract each of the energy level by this E1. So if you do that, then the E1 state, the energy of the E1 state will simply become 0. So we basically uh, recalculating or redefining the energy of each of the values: n square h square by 8m x square minus h square by 8m x square. Okay, so in that way the energy of the nth level would be n square minus 1 into E, where E is basically h square 8m x square, and that means the energy level at the ground state, that is En equal to 1, would be, or E prime 1 equal to be 0, right? So now, so we have all this thing in our hand. Now using that thing, we have calculated the partition function. So Q is basically summation over e to the power beta En Ei summation over all I. So if you put the expression of the energy here, it will give you Ei equal to the power minus beta n square minus 1 beta E, summation would be over n. So so since the energy level are very closely distributed, the gap of the energy levels are very close to each other, I mean very small. So that means we can consider, instead of considering it as a discrete energy states, we can consider it as a continuous band of energy. So by using that approximation, what is the basically advantage? The advantage is that we can write this summation is now in terms of integration, right? So integration would be from 1 to infinite e to the power n square minus 1 e beta E dn, right? Since we are doing the summation over n, so the integration will be on dn. So now, so this integration we have done. So after doing this integration, we got the expression of qx as 2 pi m divided by beta a square by half into x. So this is the expression of the partition function that we got for the given case, is that the particle is trapped and free to move inside a one-dimensional container of box length x. So okay, so this is the expression. Okay, now so similar expression, similar thing you can also calculate for 3D box also. Okay, so 3D box also, so there will be the thing, the box will be looks like this. So in that case, the Q partition function of the total box would be, so we know that for the case of a 3D box, the energy looks like this, right? E equal to E nx plus E ny plus E nz, and E nx is basically given by nx square minus 1 into E ny given by ny square minus 1 E, and E nz would be nz square minus 1 E. Okay, just the same way we have calculated energy in the previous discussion. Okay, and here instead of one, since there are three dimensions, so there will be three expression of the energy along x, along y, and along z. So now next, using this expression of energy, you can calculate the partition function. That would be looks like this. Q would be summation over n e to the power beta enx plus eny plus enz. So now if you do that, you will be getting summation over nx e to the power beta enx summation over ny e to the power beta eny and summation over nz e to the power beta enz. Okay, so if you do, you will get this this as qx, this as qy, this as qz. This would be the total q. Okay, so each of the qx, qy, qz we can easily calculate, right? Qx is basically 2 pi m a square beta half into x. Similarly, qy we'll be getting qy, we will get qz. So if you substitute all of them, you will get as q equal to 2 pi m a square beta to the power 3 by 2 into x, y, z. Okay, so yeah, so it would be give you v into lambda cube. Okay, so here v is basically the volume of the box x, y into z. This is the volume of the box, and lambda we are so lambda basically, if you calculate, if you basically do the dimension analysis of this whole quantity, we will get the dimension as 1 by L. Okay, length basically. The dimension you will be getting as length. Now lambda we are defining as the thermal wavelength. Okay, thermal wavelength is this thing basically, beta by 2 pi m by half. Okay, so this we are defining as the thermal wavelength. Okay, yeah, since lambda is the dimension of length. Okay, okay, so these are some important formulas, like the partition function for 1D, for 2D, and partition function for infinite energy ladder, uniform energy ladder. So we have calculated these quantities. Okay, so now for today's class, we'll do something different. Okay, so we'll basically now connect. So we got our main thing, that is the partition function in our hand. Now using that partition function, we are now connect the different thermodynamics properties or thermodynamics quantities. So first thermodynamic quantity that we want to connect with the partition function, that is the internal energy. Okay, so first is the internal energy. Okay, so how this internal energy is coming is basically, so this internal, like each particles are distributed in each of the energy levels, right? E1, E2, E3. So like this, E0, E1, E2, E3, right? N1, N2, N3, and N0, N1, N2, N3. So like this, each of the particles, like no, sorry, the fraction of the particles are distributed in the each of the energy levels, different fraction obviously. And so from from the distribution of the energies into each in the energy levels, distribution of the particles in the energy levels, you can calculate the total energy of the system, right? That is basically nothing but the internal energy. Okay, so the total energy would be summation over Ni into Ei. Okay. Okay. Now we can write. Now we will write this thing in terms of partition function. Okay. So how can we connect this thing with partition function? We previously knew this formula, right? Ni by n by e to the power minus beta Ei by q, right? This is the formula that we developed on the very first class, right? The Boltzmann. This comes from basically the Boltzmann distribution. So now we substitute Ni into n into e to the power minus beta Ei by q, this in here, and after doing so we get the total energy as equal to summation over n by q into e to the power beta Ei into Ei. Now this thing you can put out of the summation, n by q equal to summation over Ei to the power minus beta Ei. So now okay, so you can do some mathematical simplification here also. So one thing that you can do is that you can write this thing. So yeah, so you can write d by d beta. If you take the derivative of e to the power minus beta Ei with respect to beta, then you will be getting as Ei into e to the power minus beta Ei, right? So now this thing is, you can substitute it here, right? So by doing so you'll be getting E equal to n by q, that will be minus sign comes summation over d by d beta into e to the power beta Ei, right? Okay, now again you can take the d by d beta thing outside the summation. So d by d beta into summation over I to the power minus beta Ei. So this thing is what? This thing is nothing but equal to q, right? Q equal to summation over I to the power minus beta Ei. So this is now becomes E equal to minus n by q into d by d beta of q, right? Yeah. Okay. So this is a useful quantity. Okay. As you can see, we have now written this whole thing, the total energy or the internal energy of the system as a function of just q. Okay, so basically if you calculate the q or the partition of function of the system, and if you take the derivative with respect to beta, by doing so you'll be getting the total energy or the internal energy of the system. Okay, so yeah, this formula you can write it also like this also, minus n by q, sorry, minus n del beta of ln q. Okay, you take the derivative of ln q, you'll be getting 1 by q into dq d beta, right? So in this way also you can write this expression. Okay, so now the problem is, so this is the formula that we are having in our hand now. Now using this formula we'll try to solve some problems. So the problem number 1 is to compute E for a 3 level system, and the information that is given is that assume the system has 3 energy level. The levels are basically E0, the ground state has 0 energy. The first excited E1 is delta, E2 is 2 delta. Okay, and the others are so beta is 1 by kBt is mentioned, and the number of particles for simplicity is n equal to 1. So this is a very simple system. So for this system, we have to compute the E, the total energy. So that we will do by using the concept of partition function. Okay. So the first thing that we have to do is calculate the partition function. Okay. So Q is basically summation over I to the power minus beta EI. Okay. So now if we do the summation, we will be getting e to the power beta into 0. Ground state has 0 energy. So E0 plus e to the power beta E1 plus e to the power minus beta E2. Okay. Now it will be E0 is basically 0 into 0. E1 is basically delta, and E2 is basically 2 delta. Okay. So we got the every expression now. So we got the expression of Q. Okay, now we have to calculate the total energy E. So E is basically 1 by N by Q minus dQ d beta, right? So N is 1 and Q already know. So dQ d beta, so we'll do that. So the first stage will be 1 into the power minus beta delta plus e to the power minus delta beta to delta, right? So if you do the derivative, you will be getting 1 by Q into, there's a minus sign is also there, so minus delta e to the power minus beta delta minus 2 delta into e to the power minus beta 2 delta. Okay, so now so you'll be getting as delta, so minus would be absorbed, minus minus will become plus, so it will now become delta into e to the power minus beta delta plus 2 delta e to the power minus beta 2 delta divided by 1 plus e to the power minus beta delta plus e to the power minus 2 beta delta. Okay, this would be the total energy of the system, right, given the partition function. So from the partition function, you can easily calculate the total energy of the system. Okay. See, it's a simple system. By just you can also calculate just barely just by using the normal method. Okay. But for a complicated system, you has to use this method of partition function. Okay. Now will be, so this problem is done. Now we'll be dealing a problem on degeneracy. Okay. So problem 2 is 3-level system with degeneracy. Okay. Degeneracy means two different energy state has the same energy value, so that means that particular energy has two degeneracy. Okay. So now, yeah, so now we write it like so. A system has three energy levels that are given as E0 equal to 0, E1 equal to E, and E2 equal to 2E. And E0 has degeneracy G0 equal to 1, E1 has degeneracy G1 equal to 2, and E2 has degeneracy G2 equal to 3. Okay, so these three degeneracies are given. So by giving so having this information, first thing that we will get first thing that we'll calculate is the partition function q. Q, we know, is the summation over gi into e to the power minus beta ei. So it would be g0 into e to the power minus beta e0, g1 e to the power minus beta e1 plus g2 into e to the power minus beta e2. So from the description of the problem, we know that G0 is 1. So 1 into e to the power minus beta 0 plus G1 is 2. So 2 into e to the power beta 1 plus e, and for G2 it's 3 into e to the power minus beta 2e. Okay. So we got the expression of the partition function. We'll simplify it. So first term will become 1 anyway, plus 2 into to the power minus beta e plus 3 into e to the power minus 2 beta e. Okay. This is the expression of the partition function. Okay. So now from here we can calculate the total energy using that same formula. So E would be 1 by q into minus n dq d beta. Okay, so for this case also you consider n is equal to 1, so single particle. So 1 by q, if you do the derivative, d beta of 1 plus 2 into e to the power beta e plus 3 into e to the power minus 2 beta e. Okay, so 1 by q, so first derivative will be 0, the constant 1. Next would be 2, oh, so there's a minus term is there here, minus, so minus e to the power minus beta e minus 2 minus 3 into 6, so 6 into e to the power minus 2 beta e, so it will become, e will become 2 into e to the power beta e plus 6 into e to the power 2 beta e. Okay, divided by 1 plus 2 into to the power minus beta e plus 3 into to the power minus 2 beta e. Okay, so yeah, so this is basically the expression of the total energy. Okay, this is the way you can do for this kind of system. There is like, you can also calculate the normal way also. Okay, just like the how we do basically. So the second method is the normal method, we know. Second method, that is E, we know is total energy is basically Ni into Ei. So Ni is basically, you know, Ni by N is what we have done, Pi e to the power beta ei by q, right? E to the power minus beta ei by q. Okay, gi. Yeah. So now it would be n into gi into to the power beta ei by q. So from here also you can easily calculate. So it will become n is equal to 1. So 1 by q into gi into to the power minus beta ei. So in that case it will become, so first level has e0 equal to 0. So 0 into 1 summation, yeah, ei is also there, ei. So first energy level has 0 energy, so it will become 0 into 1 plus e into second, the g2 has 2 into to the power beta e plus g3 has 3 into 2e, the e2 is 2e into to the power minus beta 2e, right, divided by q. So if you do that, you will be getting e 2 into to the power minus beta e plus 3 into 2 to 6 into to the power minus beta e divided by q. The q also you can write is as 1 plus 2 into e to the power beta e plus 3 into to the power minus 2 beta e. Okay, so this is the expression of the total energy. So this is the normal way, the original formula to evaluate the total energy key. So by doing that process also you get the same result. We basically so this the first method, that is for this case maybe it's using both these method may take same amount of time, but the the usefulness of this first method you will only realize when you will deal with large number of particles. Okay, then maybe using this method will be much more easier. Okay, compared to doing all this summation and all, this method will be very much easier. So next problem we'll do on quantum harmonic oscillator. Okay, yeah. So this problem 3, right? uh, Quantum harmonic oscillator has energy levels En equal to h bar omega 1 plus half, where n is equal to 0, 1, 2. Then the question is find the internal energy E at temperature T. So yeah, so the partition function is okay. So here also we'll start basically from the partition function. So here there is no concept of degeneracy, so we just avoid the using the notation for G, that is to account the degeneracy. So e to the power beta ei summation is over I, so or n maybe. So now so its summation over n e to the power minus beta en is h cut omega into n plus half. Now from here, so summation over n e to the power minus beta n h cut omega into e to the power minus beta by 2. Now what you can do, sorry, beta h cut omega by 2, beta h cut omega by 2. No, we can take this beta h cut omega by 2 as the outside of the summation over n e to the power minus beta n h cut omega. So if you do the summation, you will be getting e to the power beta h cut omega by 2 into so now so summation, this thing you can write it as x to the power n, right, where x is e to the power beta h cut omega, right. So x is, as you can see, is basically 1 by 2 the power beta h cut omega. So we know e to the power beta h cut omega is very high, so in that case x is very smaller than 1, right, in generally, typically. So so we can use that in summation over the infinite series formula, right. So e to the power beta h cut omega, so it would be 1 plus x square plus x cube plus dot 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 dot. So use the summation over infinite sum. So e to the power beta h cut omega, this summation will give you 1 by 1 minus x, that is nothing but e to the power beta h cut omega into divided by 1 minus e to the power beta h cut omega. So beta h cut omega by 2, that is a by 2 term is there, So now this is the expression of the partition function we got. Okay. So so having the expression of partition function in the hand, now using that we will calculate the total energy. So first let's write that formula equal to let's write this formula for the convenience, since this exponential term is there, so it's better to use the formula which involve the log operation. So d beta into the derivative is on ln q. So so now if you do the log operation, then you will be getting ln of so inside it would be to the power minus beta h cut omega by 2 divided by 1 minus e to the power minus beta h cut omega minus d beta of ln would be ln of, you can inside the log if there is a division, you can write it as a subtraction, right, to the power minus beta h cut omega by 2 minus ln of 1 minus e to the power beta h cut omega. So like this. Now d by d beta is basically, if you take the log, so the first term you get beta h cut omega by 2 minus ln of 1 minus e to the power beta h cut omega. Okay, now so so now we will do the derivative, right. So the first term d beta, if you do h cut omega by 2 plus, if you take the derivative, you have to take the derivative with respect to ln that beta h cut omega. So if you do that, omega by 2 will be the first, then the next, if you do the derivative, you will be getting h cut omega into e to the power minus beta h cut omega divided by 1 minus e to the power beta h cut omega. Okay, so this is the thing that we will be getting after doing the derivative, the total energy term. Now from here, so this is basically the expression of the total energy. You can write it in a more compact way, h cut omega 1 by 2 plus 1 by 1 minus e to the power beta h cut omega. Sorry, if you divide it, if you multiply e to the power minus beta h cut omega on both the top and the bottom of this numerator denominator, you will be getting e to the power plus beta h cut omega minus 1. Okay, so this a very clean way you can write this expression like this. So this is how. So this is, as you can see, by using this this particular method of so this is the closed form the energy. So how we are getting basically? So we first started with the partition function. Then from there you must so here you can see, basically here you can see this superiority of this particular formula. So first you calculate the partition function q. So from there you get the very closed form, very usable form of the q from here. Now substituting that thing into the main formula of internal energy, we get the total energy as this. Okay. So, so this is the way. So this is the power of this particular formula. Just by using the, if you get the expression of Q, just take the log and take the derivative, and by doing so, you get the total energy of the system. Okay. Okay. So yeah. So now we will discuss the next problem. Suppose the partition function is given by this particular expression where a and s are constant, then what is the internal energy? The options are option A u equal to ns beta, option B u equal to ns divided by beta, option C is equal to minus ns beta, option D is u equal to n into a beta star. Okay, so these are the options given. So we'll start from the expression of the internal energy equal to minus m d of ln q by d beta. Okay, okay, so yeah, so we got the expression. So our next step would be so we also in the problem is the expression of q is also given. The first thing that we will do is the first calculate the what is ln q. So ln q is basically ln of a minus s into ln beta. Okay, yeah, so u would be internal energy would be minus n derivative of beta into ln a minus n into ln beta. So yeah, so now yeah, so now if you do the derivative, we'll be getting minus n, so d ln a will be you'll be get 0 minus s by beta, right? Sorry, plus s by beta minus minus, so it will give you s by beta. So internal energy u would be n is there, so minus n s beta, right? So this is nothing but the option C. Minus minus, yeah. Next problem is suppose the energy levels are shifted by a constant ei prime equal to ei plus e0, then what happens to the internal energy? Will it remain unchanged? It decrease by n epsilon naught, c it increase by n epsilon naught, and d it becomes temperature independent. temperature independent. So these are the options. So yeah, so okay, so we will start from the expression of the partition function. So q prime equal to summation over I e to the power minus beta ei plus e0. So since the energy shifted, so it was started from e to the power minus beta ei prime summation over I. So yeah, so now this is q prime. So from q prime, if you calculate the ln of this, ln of q prime would be uh, ln of q minus beta e0. So ln of q prime, you got the expression. So from that you will get q prime as minus n derivative of beta ln of q prime. So from here you will be getting minus n d of d beta into ln of q minus beta e0. So if you take the derivative, you will be getting minus n into derivative of ln q by d beta minus e0. So that means, as you can see, initially the q was basically e to the power minus beta e0. So for that case, u was, if you calculate u, it should be n into d of ln q by d beta, right? Minus, obviously. Now for this case, so this case, as you can see, it would be minus n of d ln q by d beta minus e0. As you can see here, the energy, the total energy or the internal energy shifted by e0, right? Or n is 0, sorry, n is 0. The n is outside, okay, so n into e0, yeah, plus plus minus, yeah, so n into e0. So u prime is basically u plus n e0. So the amount of energy that gets shifted is the amount is n e0. So the correct option is increase by amount n e0. Okay, the option C. Option C is the correct answer. Okay. So now, so we get pretty much the concept of the total energy of the system. So now we'll be getting the internal energy. So there is there's a small difference between the total energy and the internal energy, and that is that uh, uh, when we go from the total energy to the internal energy of the system, we have to add the total energy with a 0 point energy. Okay. So by doing that, we'll be getting the internal energy. Okay. So how to do that? So the internal energy U would be U0 plus E, right? So E is basically minus N by Q dq d beta. Okay. So here, so what we have done is that we are trying to get internal energy from total energy. Okay. So to do that, what we do? We need to add the 0 point energy that is u0 basically to the total energy of the system, to the that is E. Okay. So by doing that, we will be getting the full the form is the basically the addition of this 0 point energy with the total energy gives us the internal energy of the system. So yeah, so now we can write it like this. Q is equal to u0 minus n by q del q del beta at constant v, or you can write it like this also, u0 minus n into del ln q by del beta at constant v, whatever the way. So now the next thing is that is okay, so yeah, so now if we consider that in the previous class we have discussed the partition function. Let's suppose a particle that is trapped inside a box. In that case, 3D box, let's suppose a particle is trapped inside a 3D box with a finite volume V. In that case, we have derived the expression of its partition function, right? And what is that expression? That expression is basically given by Q equal to V by lambda cube. Okay. So in here also we assume that the particles are basically trapped inside the in the box, 3D box, while inside the box it can move freely. So it's a free particle inside the box problem. So for that, the Q is basically V by lambda cube, we know. By lambda we have defined it as the thermal wavelength. The expression is beta h square by 2 pi m to the power half, right? This was the expression of the lambda thermal wavelength. So now if you substitute this into this expression here, you will be getting u minus u0 equal to minus n by v by lambda cube into del beta of v by lambda cube. Okay. Now from here, so lambda is a function of beta, so it will give you minus n lambda cube by v into minus 3 by lambda to the power 4 into delta lambda delta beta at constant volume. Okay, so now if you do the calculation, you'll be getting the expression as 3n by lambda into 1n by 2 into, so if you do the derivative with respect to lambda, it will give you beta h square by 2 pi m half into beta h square by 2 pi m into 1 by beta. Okay, so u minus u0, q minus u0 you will be getting as 3n by 2 beta into 1 by lambda into lambda. So this gives you u minus u0 as 3n by 2 beta. Okay, so you will be getting u0 plus 3n by 2 beta. Okay, this is the expression for the internal energy for a particle that is trapped inside a 3D box. Okay, so this is a very useful quantity. So okay, so yeah, so this is the expression of the internal energy. Okay. Okay, so now, so next thing is a specific heat. Okay, now we'll calculate the specific heat. Okay, so the formula of specific heat looks like this. We know first we will first write the expression of the specific heat, and then we will write it. Yeah. So then we'll try to write it for a monoatomic gas. Okay. So yeah. So first, this what is specific heat is. So first we just write it. So specific heat or heat capacity of a monoatomic gas. Okay. So here we'll mostly considering a specific heat at constant volume. Okay. Because the specific heat at constant volume directly depends on the change in internal energy. Okay. So how does that two quantity relates with each other, that we will see. So specific heat is basically that temperature, sorry, the heat that is needed to raise the temperature of given system by an amount delta T. So mathematically you can write it like this: C equal to dq by dt at constant volume. Now from the first law of thermodynamics, dq equal to du plus dw, du plus pdv. Since this thing this specific at constant volume specific heat we are calculating, so this dv is basically is equal to 0. So dq you will be getting as du. So dq equal to du, so you can write it as du by dt at constant volume, that is as Cv, right? So yeah, so now as you can see, Cv thing we can write in terms of in terms of this specific heat. Sorry, internal energy. Okay. Okay. Now, so we know that U is U0 by 3n2 beta. Okay. So you can write it as this: U plus U0 plus 3 by 2n kBT. Okay. Or you can write it like this also: U0 plus 3n by 2. So n you can write it as n into Na into Kb into T. So Na into K is nothing but the ideal gas constant, that is the R nRT, 3 by 2 nRT Cu. So now Cv is du dt at constant volume is equal to Cv 3 by 2 nR. Okay. CV is basically 3 by 2 nr. Okay, so you got the expression of CV here. Yeah. Okay, so this is the expression of the specific heat for a monatomic gas. Okay. Now CP as actually cannot write it because CP is not directly related to the change in internal energy. So okay, so that's why we are only interested in species CV, that is a specific heat constant formula. The CP formula looks like this actually. So CP formula is connected with the change of enthalpy actually. Okay, so we know that H is basically the enthalpy. H is equally U plus PV, right? So dH is equal to du plus PdV plus PdP. So yeah, du plus PdV, this thing can write it as dq plus PdP, so dH. So now dq is basically dH minus V dP, right? So the specific at constant pressure Cp is basically dq by dt, right? Now at when P is constant, so that means that this dP is equal to 0. So only term that survives here is that dH by dt, right, at constant pressure. So as you can see, it's related with the change in enthalpy, not related with the change in the internal energy. So for that, we cannot really use the concept of internal energy here to get the expression of Cp for the monatomic gas. Okay, yeah. So yeah, so by basically in experiments, you can use this change in internal energy and with temperature, and by doing so, you can calculate the specific heat. Okay. There are specific instruments are there to calculate basically this change in entropy in the systems. So yeah, so your next problems, we'll now do some problems on this topic. So the first problem is so starting from u equal to minus n delta of ln q by delta beta, which expression gives the constant volume heat capacity. Okay. Option 1 is Cv equal to n by del square ln q by del beta square. Cv equal to minus n kb beta del square ln q del beta square. 3 is Cv equal to n kb beta square del square ln q by del beta square. And option 4 is Cv equal to minus n kb beta square into del square ln q into del beta square. So these are the 4 options are given. So the Cv expression for Cv expression, so from the expression of the internal energy is given. From that we have to find out the expression of Cv. That is, we just have to use the formula and a bit of mathematics to get the result, get the answer. So Cv is, we know the formula del U by del T at constant volume. So yeah, so if you do that, so U is now a function of both Q and beta. So U Cv is so this is the derivative. You can write it is like that, chain rule, du by d beta into d beta by dt, right? So here beta is basically 1 by kBt. Okay, so instead of writing in terms of t, we will write in terms of beta. Okay, since in the expression of u it's written in terms of beta. So beta is this, so d beta by dt 1 by kb t square. So that is nothing but minus kb beta square, right? So d beta dB will be uh, minus k beta square into du d beta. Okay, so u is minus n t of ln q d beta. So du d beta is minus n d square ln q d beta square. So just plug it into the expression of c du d beta. So cb will become minus n kb beta square d square ln q d beta square. This is the expression of cv. Okay, so minus, there's a minus means it will become plus. Okay, this is basically the expression of cv that we are getting, cv. Okay, so the way is pretty simple. Just get the expression of u, from there take the derivative of du d beta, and you will get the expression of cv. Okay, next problem is problem 2. Monoatomic gas has internal energy ut equal to u0 plus 3 by 2 nRT. Suppose we have suppose two different gases have, suppose two suppose two different gases have u1 0, that is the 0 point energy basically there, 1000 joule, and u2 0, the 0 point energy of each of the gas. Okay, 5000 joule. Now calculate cv for each gas. Okay, the first problem is a, calculate cv for each gas, and b is calculate the change in internal energy when each gas is heated from 300 Kelvin to 500 Kelvin. Okay, yeah, so the problem is the okay, so the expression of the internal energy is given. U T is basically U0 plus 3 by 2 nRT. Now CV is a specific heat, that is du by dt at constant volume, which is dd dt of u0 plus 3 by 2 nRT. So CV equal to 3 by 2 nr. Okay, so this is the expression of the CV basically. So yeah, so as you can see, this is just a constant value. Okay, so it depends upon the mole. Okay, so both contain 2 mole of gas. Okay, so that I have not mentioned, actually in the problem it's mentioned. So both contain 2 mole gas. Okay, so that means the specific heat for both of these two gases would be similar, right? So so if you know, so n equal to 2, that means, and R we know is 8.314 joule mole inverse Kelvin inverse. So substituting it, you get CV equal to 3 by 2 into 2 into 8.314 will give you 24.94 joule per Kelvin. Okay, so this is the value of CV, and it is equal for both the gases. Okay, so both gases have exactly same heat capacity, heat capacity. Okay, yeah. So yeah, so the next, this is the first problem of problem A actually. Okay, so problem B is you have to calculate the change in internal energy. Okay, when the temperature rises from 300 to 500 Kelvin. Okay, that is also easy. So we know ut is u0 plus 3 by 2 nRT, right? So u 500 minus u 300 would be 3 by 2 nr into 500 minus 300, right? So 3 by 2, sorry, 3 by 2 nr into 200, so delta u, that would be 3 by 2 into 2 into 8.314 into 200, which gives us delta u. So delta u is 4988.4 joules. Okay, okay. So now we will be now jumping to So now, so far we have kind of only mainly focused on the internal energy of the system, how the internal energy is related with the partition function. Now we are be focusing on how the entropy of the system is related with the partition function. Okay. So yeah. So now our focus will be on mostly on entropy. So the thermodynamic definition of the entropy is this: dS, that you all know, dS equal to dQ. The change in this equality only holds if the dQ is a reversible process, dQ by T. Or you can write it for at constant volume. If it is constant volume, you can write it as du by T. Okay, remember, for constant, it's only applicable at constant volume. Okay. So now, okay, so that means for constant volume there is a direct relation between the change in entropy and the change in the internal energy. So now we'll be using this fact. Okay, so for that, first let's write the internal energy expression equal to U0 minus plus E. So U0 plus E is summation over Ni into Ei. Okay. So GU will be now become summation over I Ni dEi plus summation over I Ei dNi. So this should be coming, so du0 is 0 and Ni Ei di is, that is, yeah, that is given. So yeah, and Ei, the energy, the energy of each of the levels is also fixed, so dEi this time will also become 0. So du is basically summation over Ei dNi, right? So now so you'll use this thing here. So now ds is du by t equal to summation over I Ei dNi by t. Now from here, so we here, so in the first class you remember that we have this for when we derive the expression of this Postman distribution. So for do that, in order to doing that, we have written the concept of configuration or the weight of a system, and we have write a relation, differential relation, how the weight of the relation is basically related with the energy, and alpha and beta, that's are basically Lagrange undetermined multiplier, right? So that expression looks like this actually: delta ln W by delta Ni plus alpha minus beta Ei equal to 0. This expression you remember from the first class. Okay, so the reason that we are using this relation is basically, so instead of write the entropy as a expression as a summation term, we will basically use this relation and try to write this expression of the entropy in terms of the weight of the distribution. Okay, so in order to do that, what we can do is that, so we can write from this relation the beta Ei is equal to delta of ln W delta Ni plus alpha. Now if you substitute this thing here, you'll be getting, so the kBt is there, so we can multiply kb numerator and denominator. So kb will be coming outside the summation, so delta ln W plus delta Ni plus alpha into dNi, right? Just basically substituting this thing here into the main expression. So okay, now the next thing we multiply dNi, so ds would be in summation over delta ln W delta Ni into dNi summation over I into summation over I alpha into dNi. So if you do that, we'll be getting summation over ds summation over k I delta ln w delta ni into dni equal to dni will cancel to become ln of d of ln w. Okay, derivative of ln w. This is basically the expression for the change in entropy. So this is in differential form. It's if you write in normal form, it will looks like this. This is basically k into ln w. Okay, so this w is basically given here is the weight of the most probable configuration of the system. Okay, so that means if you can calculate the weight of a particular configuration, you can calculate the entropy corresponding to that configuration. Okay, and for doing, in order to do so, you have to just use this formula of the entropy. The change in entropy you can also calculate. Okay, so you can also write it in different form also. Okay, you can also write the entropy in terms of specific heat also. Okay, there are different formulas. Okay, this is one formula. Another formula is this: ds equal to ds equal to dq reversible by t, that we know. Dq reversible, you can write it as du by dt, du by t, right? Du, you can write it as cv dt, right? Basically cv, you know, du by dt. So from there we can write it like this by t. So if we integrate it, we will get the s2 minus s1 is basically cv by t dt integration t1 to t2. Okay, so this way you can calculate that by getting the temperature of two different states, you can calculate their change in entropy. Okay, okay, so this is the way. Another way is okay. So now so next thing that we'll do, you can write, you can write this expression of the entropy in terms of specific heat, or in terms of total energy, as well as in terms of the partition function. Okay, so far we get the formula in terms of weight. Now since weight is not a very not a quantity that can be easily calculated, right? So the quantity that can be easily calculated for a system is the quantity like specific heat or partition functions. So for that reason, for a realistic system, the entropy we will try to write in terms of those quantities that can be observed or that can be calculated easily. Okay, so we'll start from that original formula. So S equal to kV ln W. So W is the weight, that is we know that the expression of ln W, you know, basically ln W is nothing but n into ln n minus summation over ni ln of ni, right? It's coming from basically this formula, W of n factorial by n1 factorial n2 factorial, like this. So from this formula it's coming by using the Stirling approximation, right? So if you substitute it here, you'll be getting S equal to KB. This N you can write is summation over I Ni ln N minus summation over I Ni ln of Ni. So from here you can write it as S equal to KB. And take K as common. Summation of summation you can take it outside, Ni into ln N minus Ni into ln Ni. Now from here you can write it as S equal to minus KB summation over I ln of Ni by N. Okay, so yeah, you can write it in more simpler way, KB by N into, so there is a Ni outside also here, yeah, summation over Ni by yeah, not here, like this, minus N KB summation over Ni into Ni summation over ln Ni by N. Okay, now this quantity you can write it as minus Nk. So Ni by N is nothing but Pi, right? Probability. So Pi into ln of Pi. Okay. So Pi is basically Ni by N, that is e to the power beta di by q, right? So to substitute these things here. So by doing that, so you'll be getting S equal to minus Nk summation over I. Pi would be, let's just keep the Pi as this, and this term will become ln of e to the power minus beta ei divided by summation over I to the power minus beta ei, right? So if you do that, or you can write it as q also, yeah, ln q for the time being. Okay, so now if you do that, you get minus Nk summation over I Pi minus beta ei minus ln q. So minus Nk summation over I Pi beta ei. Minus minus will become plus. Again minus minus will become plus Nk summation over I Pi ln q. Now from here Nk summation over I Pi would be Ni by N into beta ei plus Nk summation over I. So ln q can take it as common, ln q summation over I Pi. Now if you do the substitution here, so you get Nk, you can take beta as common, summation over I Ni ei plus Nk Ni by N is also there. Okay, so N by N. So N into K ln Q summation over Pi. Summation over Pi is nothing but this thing will be equal to 1. Summation over of that will be 1, right? So this side it will be getting 1 by T summation over Ni ei summation over I into Nk ln Q. So this thing is nothing but E, total energy E by T plus Nk ln Q, that is the entropy as of A. So this is the expression of entropy that we will be getting. Okay, yeah, so started from the expression for the weight, we get the very useful expression for entropy in terms of the total energy. and the partition function of the system. Okay, so yeah, so we can write it in terms of internal energy also, like this is equal to u minus u0 by t plus nk ln q. Okay, this we also can write. Now we'll do some problems related to that. Okay, first problem is problem 1. Consider n particles identical, independent, three level systems whose single particle energy levels are single particle energy levels are is equal to 0, E1 equal to E and E2 equal to 2E. Show that the heat capacity at constant volume CV is what they have to find out basically. Okay, so yeah, so the energy levels are this, so 0, E and 2E, these are the three energy levels, right? So now the first thing that you have to calculate is the partition function of the system. Okay, so here single particle, first we calculate the partition function for the single particle. Okay, so Q would be summation over I e to the power minus beta ei. Okay, so it would be 1 plus e to the power beta e plus e to the power beta 2e. Now, so now we can write for our easiness of calculation, you can define e to the power beta e as x. So in that we can write q as 1 plus x square. Okay, so okay, so you got the expression of q. Now from it you can calculate the internal energy. So internal energy, u, we know the formula, minus n z then beta of q, right? So n is the number of particles. So here we have a finite number of particle n, and that has to be identical. That particles has to be identical in order to validate this particular expression. Okay. Oh, sorry, it should be long q. not single q, ln q. If you do that, so minus n del beta of ln 1 plus x square. If you do the derivative with respect to ln x, del beta of ln 1 plus x square, if you do this thing, you'll get 1 by q into del beta of q, that is 1 plus x square. Okay, so x are nothing but a function of beta, right? E to the power minus beta e, right? This is basically x. So if you do the derivative, you'll get 1 by q, so del beta of x plus del beta of x square. So del beta of x is nothing but minus e to the power minus beta e, and del x square is nothing but minus 2e into e to the power beta 2 beta e, right? So this will be get, so from here, so that means del beta of ln 1 plus x square is minus e x plus 2x square divided by z, the partition function z. So now okay, so now u would be minus n into del beta of ln z equal to n epsilon into x plus 2x square divided by 1 plus x square. Okay, so we got the expression of u. So now from the expression of u, we can calculate the expression of cv, right? So we know uh, cv is, yeah, so x is e to the power minus beta e. Okay, that you have to remember. So cv we know is du by dt. Now we have shown that since u is a function of beta, so it's better to write this derivative in terms of beta, not in terms of t, right? So if you convert it, it will be, looks like this. We have done it earlier. So it will looks like this, du d beta into d beta dt. So d beta dt is nothing but minus 1 by kt square into du d beta. Okay. Now if you do the du d beta, so it will give you cv equal to minus 1 by kt square. So du d beta is, du d beta means u is this thing, n e into x plus 2x square by 1 plus x square, right? Now you have here, from here you have to do the derivative, right? So for do that, first what you can do is you can take ne outside, minus ne by kt square. Now you can take the derivative, d beta equal to x plus 2x square into 1 plus x by x square, right? Now from here, if you do the derivative, you will be getting nk into beta e whole square into x plus 4x square by 1 plus x square minus x plus 2x square whole square by 1 plus x square. This things whole square. Okay, but x equal to the power beta e. Okay, cv. So now yeah, so this is the expression of cv. So if you simplify it, cv will become nk beta E squared x into x squared plus 4x plus 1 divided by 1 plus x squared whole square. Okay, so this is the expression of CV we get. So this is how we can calculate the specific heat. Here x is e to the power beta. If you substitute the expression of x here, you get the full expression of CV. Okay, so that is how we can calculate basically. So basically the main thing of this problem is started from the partition function, and from there itself we have calculated first the internal energy, and from the internal energy we got the specific heat. Okay, so this is the last problem, so I will be ending our class.